I am a professor. I'm going to share my screen. Professor of astronomy at Yale University, and I'm going to talk to you today about some of the fundamentals of radial velocity precision, with the idea that in 20 minutes I really can't tell you what it takes to find low mass planets. The outline of my talk is this. I want to talk to you a little bit about the progress that we've had to date, and to emphasize that we have good recovery of Jupiter and sort of to Neptune mass planets, but that I would argue that Earths at all separations are really missing from precision radial velocities. There are a few exceptions, and these tend to be around low mass stars. I'll come back to that. And then I want to talk about why it's difficult, why it's been so hard. Well, 0.2 kilometers per second, Otto Struve's prediction, is 1/5 of a pixel shift. So you've got a stellar line which spans many pixels, and you're trying to measure the back and forth amplitude, where the amplitude is only 1/5 of a pixel. That's for 200 meters per second. For an Earth mass planet, the radial velocity that's induced is about 10 centimeters per second, and that's 1/10,000th of a pixel shift. So with the current state of the art precision of 1 meter per second precision, it just hasn't been possible. And then I want to touch a little bit on the future of EPRV, extreme precision radial velocities. There are two instruments that have already been commissioned now for a year or two. That's Express and Espresso, and I can show you some results there that we're reaching 25 centimeters per second. And there are other instruments that are on the horizon, notably NUID, which should be commissioned soon, and the Keck Planet Finder. Okay, the progress to date in this plot sort of shows what we've been doing for the last 25 years. So this plot shows the planet mass, or rather M sin I, in units of Earth masses, and the year of discovery. And you can see that it looks like with time, right, the blue dots are getting down to lower and lower mass planets. I've stenciled in, you know, where Earth, Neptune, and Jupiter would be roughly on this plot. And I want to divide this figure into a zone that shows that the real advance here, in my mind, was the construction of the HARPS spectrograph. So a stabilized spectrograph in a vacuum enclosure really made a big difference for the field. If we look at these lowest mass objects, it looks like we're really continuing to improve in precision, but in fact, most of these objects are orbiting low mass stars. So the gains that you see here don't reflect an improvement in radial velocity precision. They reflect an improvement maybe in strategy, where people are saying, you know, let's look at low mass M dwarfs because the velocity amplitude from an Earth mass planet will be larger. So that's how people have continued to push the field. So I think the takeaway message here is that HARPS really advanced the field from roughly 3 meter per second precision to 1 meter per second precision. And there haven't been any notable gains in RV precision until about 2019. So from 2003 to 2019, everybody was just struggling to get to 1 meter per second RV precision. Now we have this incredible results from mostly from Kepler. Again, now we have planet radius on the y-axis, and again orbital period. And I've again put in with dashed lines the location of Earth, Neptune, and Jupiter. I'm going to divide this plot into 3 zones: the blue, so the massive planets; the orange, the planets with masses between Neptune and Jupiter; and the green, the sub-Neptune mass planets. You see here sort of a trend in the green zone, a fall off, and that fall off is partly because of the failure of 2 reaction wheels on Kepler, so we lost the pointing of Kepler in that field, but also reflect a sensitivity of the transit probability to the semi-major axis. So no matter what, even if Kepler had continued to run, there would be a few more dots there, but it was going to be harder to find those planets. We can calculate the ratio of planets in each of these zones, and I'm going to normalize to this middle orange zone. And we get the numbers say roughly, you know, 2 to 1 to about 8 in the green zone. So Kepler told us that the low mass planets, the small planets, far outnumber the Neptune to Jupiter mass planets and greater. If we looked at the same plot in radial velocity, now again, planet mass on the y-axis versus orbital period, but imagine that we have an instrument that delivers 2 meters per second precision. This is the sort of underlying population that we would see for exoplanets. And you can see that this misses all of those planets found from Kepler. If we look here now and say that all of the planets with amplitudes greater than 3 meters per second would be detected. We have a smaller sample size with radial velocities, right? We're looking at stars one by one. Kepler was looking at a field of 155,000. But you can see that it wasn't possible to really detect many planets with amplitudes smaller than about 2 or 3 meters per second when we had sort of 2001 precision. The planet ratio here is roughly 0.9 to 1 to 0.7. Okay, 0.7 means that if your spectrograph is delivering about 2 meters per second radial velocity precision, you're missing 92% of the planets that are in the green zone. All right, now what if your instrument delivers 0.8 meters per second precision and you can take many observations? We look at these regions again. There's our old so 1999 precision that delivered velocity amplitudes greater than 3 meters per second. And now with 0.8 meter per second RV precision, we can get down to about 1 meter per second RV amplitudes. Okay, this means that in each of these zones, we have a ratio of the massive to middle to lowest mass planets, 0.9 to 1 to 2.5. Okay, that means that if your spectrograph delivers 0.8 meters per second RV precision, you're still missing about 70% of the planets in the green zone. If we could build a spectrograph that has 0.2 meters per second precision, and if we can develop statistical methods, which I will claim are on the horizon, to disentangle photospheric velocities from center of mass velocities, we should be able to recover the Kepler exoplanet statistics. So this dashed line is where we want to go to be able to detect velocity amplitudes down to about 0.2 meters per second. Okay, the obstacles to higher precision are outlined in many places. One is this State of the Field for Extreme Precision Radial Velocity paper from 2006. But basically, they fall into 4 different categories. The first is instrumental stability. The instrument has to be temperature stabilized, pressure stabilized. We have to do precise wavelength calibration. The detectors, modern detectors, have a lot of problems, and there's not a lot more R&D that's going into detectors, so that's a worry. The second category is the information content of your spectra. What's the signal to noise? What's the resolving power of your instrument? What's the observing cadence? Do you only get telescope time 1 or 2 nights a month, or do you get time every single night? And then what's the total number of observations that you're acquiring? All of these things are critical. Then the third category is analysis errors, and these would include things like your ability to model the Doppler shifts. So understanding the impact of the line spread function or the PSF point spread function, to understand telluric contamination and to model it and model it out. And then the ability to extract signals from noisy data. So everything in here matters. The fourth category has really, I think, stalled the field for a long time. People have been sort of stymied by the idea that astrophysical noise is going to limit our precision. And it actually kind of prevented us from, I think, moving forward with new spectrograph designs, at least for a while. Fortunately, we've done that. But astrophysical noises would include spots on the surface of rotating stars, pulsations of the star, granulation, meridional flows, long-term global magnetic cycles like the solar cycle. In general, in the past, we've diagnosed astrophysical noise with calcium 2 H and K line core emission, with line bisector variations, with emission in the core of the H-alpha line, and by looking at the full width half max of the CCF. So these are all sort of global. You have the whole spectra, and you distill the information about astrophysical noise into a few parameters. It's not really, it's a kind of, I would say, a blunt knife for solving this problem. One of the papers that really gave me a lot of hope, I think, in this field was, that there's a lot in these plots, was Davis et al. 2017. So Alan Davis ran PCA, principal component analysis simulations on SOAP spectra. So these are simulated spectra, and assumed that there were either injected spots or faculae into the spectra. And then in each of these subplots, there is a grid of simulations that runs at different spectral resolving powers, that's on the x-axis, or signal to noise, which is on the y-axis. And the top row shows features that are 5% of the star. Those are very large features. The middle row, 1% features. Those are still relatively large. And then the lower row shows that for stars that are very quiet and have surface features of about 0.1%. Do we have the ability to extract information? That is, the number of principal components is a metric for how much information there is about the spots or the faculae at different resolving powers and different signal to noise. So in the olden days, back in sort of 1997, 2000, we were working with spectrographs that had resolutions of about 55,000 and signal to noise of about 200. And you can see on those bottom plots, there was just not enough information to be able to separate the orbital velocities from to see the activity. So this is telling us that we need to drive, I think, towards higher signal to noise, higher resolution. And I would say the one thing that's not captured here is also extremely high cadence. That cannot be underestimated. We designed and commissioned Express, the extreme precision spectrograph, at the 4.3 meter Discovery Channel Telescope. The name of the telescope has recently been changed to the Lowell Discovery Telescope, LDT. And our precision goal for the instrument was 20 centimeters per second. So that doesn't include anything about stellar activity. The instrument was funded by the National Science Foundation, and the total cost of the instrument was $6 million. There is a whole list here of unique features, and I would be happy to answer questions about them, but I'm afraid that if I read through this whole list, that I won't have time to get through my 20-minute talk. I'll just highlight that, to me, the most important, impactful decisions that we made were to use a laser frequency comb, which has been working beautifully, and to push up the resolution of the instrument to 140,000. But everything on this list is important. And maybe the last item is the third thing that I would say, is that the LDT, the Lowell Discovery Telescope, has a deployable tertiary mirror. And that means that in 60 seconds, we can move from one instrument on the telescope to Express. And it means that we can strategically schedule our observations, which has been important. Express has a fiber agitator, which you see here. It's kind of comical. These two arms have different lengths, so they're oscillating at different periods. That chaotic oscillation of the fibers produces excellent scrambling of our fibers. And I'll just show you how bad things were, just so you know you shouldn't despair when you first turn on your spectrograph and something looks bad. In December of 2018, we took an hour of laser frequency comb observations and cross-correlated them against each other. And what we saw, expected to see, 3 centimeter per second precision, just flat, and instead saw this huge sinusoidal signal. It was just absolutely frightening. And this was identified by someone on my team, Andy Shemkoviak, as a beat frequency between strobing of the spatial light modulator in the laser frequency comb and vibrations in the cryocooler for our detector. So Andy went in, reprogrammed the spatial light modulator to run at 55 hertz, and the beat frequency went from a 6-minute signal to a sub-second signal and essentially washed out. Okay, so we took care of the beat frequency, and we then turned on the laser frequency comb and took observations. And you can see the middle blue section in 2019 shows modal noise in our fibers because the fiber agitator had tangled with the fibers. And fortunately, we used a low torque motor. And so as soon as they felt any resistance, they stopped. But without that agitator, the RMS of the laser frequency comb was 30 centimeters per second. So we redesigned the fiber agitator, got up and running again in February of 2019. And now the RMS of the laser frequency comb observations over an hour is about 5 centimeters per second. So in some sense, this reflects the instrumental precision. This is the laser frequency comb going through the fiber, being fed to the spectrograph and observed, at least short term over an hour or so. So to get down to 10 centimeters per second, it's just all about calibration. We have two fibers, an octagonal fiber, which is then pupil sliced so that the circular pupil image becomes two half moons, which are stacked and injected into a rectangular fiber. And so what you see here are the image of our rectangular fiber illuminated with the laser frequency comb. And it's kind of making my eyes cross to look at this. So I think I'm gonna go on. But the laser frequency comb gives an incredible wealth of information to calibrate the instrument every 10 pixels. There's a line when we extract the laser frequency comb. We do a peak, use a peak finding algorithm, fit the peak, and then extrapolate or interpolate to get a wavelength solution at every single pixel. Those laser frequency lines are known to, with a precision of something like 10 to the minus 12. They're used by atomic physicists, so it's incredibly precise. We're moving to a new approach with our fitting of the laser frequency line with a code called Excalibur. Lily Zhao, who's my grad student, worked with David Hogg and Megan Bedell at the Flatiron Institute, and developed a principal component analysis that looked for low order transformation. Express drifts by about 1 meter per second over a full night. And so that means that fitting each LFC independently just presents opportunities for noise. Instead, we'd like to use the accumulated wealth of LFC observations that we have and just allow them to slowly transform through the night. So I'll just flash by a few results. So here are some stars that we observed in 2009. And sigma internal is a measure of the formal single measurement precision, and the RMS is the scatter in the velocities over whatever timeline is shown on the x-axis. So the RMS here is about 70 centimeters per second, and our internal errors are about 20 centimeters per second. Here's another star, yeah, that another star, two stars with the same name, something's wrong there. So here, ridiculously low scatter, but a relatively short time baseline. Another case where we're at about 15 centimeter per second measurement precision, and over a month or two, the RMS is about 25 centimeters per second, another star. So we could just sort of flip through these, and I was really interested to look at Tau Ceti. When I observed at Lick Observatory, Tau Ceti was the poster child for high precision because we got the lowest, RMS for Tau Ceti than for any other star. But here you can see that the internal errors are about 10 centimeters per second, but the RMS over a couple months is about 1 meter per second. So what's going on? Well, the points that I'm showing you are actually nightly binned data. And if we zoom in and looked at all of the data that comprise the binned data point, you can see that there are P mode oscillations in Tau Ceti that in the case of the lower left plot are actually remarkably large in amplitude. The coherence of the P modes come in and out of resonance. So Tau Ceti has turned out to be not our poster child. We'll find a new one to replace it. When you write a proposal for spectrographs, you make your best guess about what the radial velocity errors are going to be, but you actually don't know. You haven't built the instrument yet. You haven't tested it. So it's a funny game. And then once you do take observations, how do you know what fraction of your errors are coming from the instrument, the star, the fiber, you know, all of these contributions. So my student Ryan Blackman wrote a nice paper in 2020 where he goes through, his job was to actually try to isolate as many of the RV error contributions as possible to express, excluding stellar activity. And he summarized here in this plot below that our instrumental errors are less than 10 centimeters per second. The photon noise at a signal to noise per pixel of 250 per resolution element. We have 4 pixels per resolution element, so that would be a signal to noise of about 500 per resolution element. Our errors are about 30 centimeters per second. So Express is performing just the instrument on star, but not including stellar activity, is probably under 30 centimeters per second. And I think we see that in some of the data sets that we've shown. We have a benchmark that we're proposing for the EPRV community, and it's the star, to observe the star HD 3651. We observed it for about 6 months. The star is bright. It has a visual magnitude of 5.88. It has a declination of plus 21. That makes it accessible from the north and from most of the southern hemisphere observatories. The star has a known planet. The planet is roughly a Saturn mass with a period of 62 days. But the remarkable thing about this orbit is that the eccentricity is 0.6. That means that this planet is sweeping in and out, close to the star and farther away. And it's dynamically clearing away any small planets that might exist, as the simulations by my student Sam Cabot showed. So there's still going to be some granulation, some activity from the star, but we've eliminated one of the possible error terms, right? We can't say, oh, the radial velocities are changing and maybe it's because there are small planets. No, in this case, any long period planets would just be a gentle trend to the data. So here are some examples of now a comparison of what we've done. The top plot shows you HD 3651 using Keck high-res data, which was published by Paul Butler et al. In 2017. The individual error bars on the 10-meter Keck telescope are about 1.2 meter per second. And the RMS to the model fit, this is over many years, is about 3.4 meters per second. The lower plot shows the results for Express. So our error bars are about 25 centimeters per second, and the residual RMS to the model is about 60 centimeters per second. You can, one thing I want to point out is the advantage of the deployable tertiary and the ability to schedule observations quickly. It's really difficult to catch periastron passage in this very eccentric orbit, and you can see in the Keck data with something like 10, 15 years of data, there are only a few points on that rapid rise. We were able to get schedule an observation. So call up the telescope and say, could we just have 10 minutes of your time tonight? We'll trade you. And we were able to nail those data points during periastron passage. So the advantage of high cadence just cannot be overestimated for pulling out complex signals. But so this is a benchmark. I would love to see other spectrographs, what they can do. Will espresso sort of beat this result? And it's a comparison, right? It's not really a contest, a personal contest. It's just to try and figure out what instruments we need, what designs we need, so that we can really push down to higher precision. I wanted to show this nice result from the Geneva team. This is data from Espresso for Proxima Cen B. And there's, on the top plot, you see data from UVES, from HARPS, and from Espresso, two different eras of Espresso. So the filled circles, green circles for Espresso, show its current precision and configuration. And like, you can just see what an incredible difference that high precision makes. That yes, with HARPS and 450 data points, you could model this signal. But with Espresso and this high precision, you only need a few dozen points. So you really get there more quickly. Now, one thing to think about, and I hope you will ask Vinesh Rajpal in his session on Gaussian process regression, is that the team did use GPs, and GPs will tend to drive down, they absorb some of the red noise. But in any case, you can see that the residuals in the bottom panel show that espresso is getting 30 centimeter per second residual RMS compared to HARPS at 1.3 meters per second and UVES at 80 centimeters per second. So there really is a fundamental, I think, shift in precision that's due to this new generation of instruments. In summary, the 1 meter per second precision radial velocities have been successful in detecting Neptune to Jupiter mass planets around nearby stars and some lower mass planets around later type stars. There's a new generation of EPRV instruments online, including Express and Espresso, and soon NUID and KPF, the Keck Planet Finder. And these instruments I expect will deliver EPRV precision of about 25 centimeters per second, 10 centimeters per second in the best case. I want to tell you that the Menlo laser frequency combs are now turnkey. However, it's desirable to have similar precise calibration blueward of 500 nanometers, so that still is one area of technology to work on, and that there's been significant progress on using statistical methods to disentangle photospheric RVs from orbital RVs. And then my final point is you have to get everything right. There are 100 things that can go wrong, and if you only get 99 of them right, it might not be good enough. And this is everything from the instrumental stability to the extraction, flat fielding, wavelength calibration, telluric modeling. But the point is that we are making significant improvements. We've taken the step now to a new generation of instruments. And I think that precision radial velocities are, until we launch a LUVOIR type instrument, are the only way to get down to, close to Earth like planets around maybe K-dwarfs. So thank you.
Thank you, Deborah. That's a great talk. And it looks like we have a lot of questions, so we'll try to get through as many as we can. First one is, so 20 centimeter per second precision is really incredible. Are these values, are these RVs, sorry, I'm trying to interpret. Yeah. The precision of these values without any RV correction applied, I guess like from the Davies technique, is this just raw out of the pipeline? And if yes, don't we expect stellar activity to produce jitter that's much higher than this on a timescale of several days?
Yep, good. Okay. Yes, so these, there are no corrections that have been applied to the radial velocities. This is something that we're hoping to do that will make things even better. And we actually have run, we're not quite ready to announce, or we have papers in the work that actually show that, we can make progress on reducing the RMS scatter even more. So the question was, don't you expect stellar activity to kick in? And the answer is yes, but stellar activity probably changes on relatively slow timescales, right? So spots will persist for 1 or 2 rotation periods. And all of the data that I showed you were relatively short periods. They were a month or 2 months in the case of HD 3651. And 3651 is a K-dwarf that's chromospherically inactive. So that's a particularly good case for a whole bunch of reasons.
Okay, so this question came up several times, probably because of the presence of neowise in our sky. So can we use the PRV method to detect comets around other stars?
So it's all about mass. If you look back at the equations that Chaz Bender showed, the radial velocity amplitude for Earth is about 9 centimeters per second, and that velocity amplitude depends on the mass of the planet, the sign of the inclination, the mass of the star, the eccentricity, and the orbital period. So in the case of comets, the masses are just too small to be able to detect. We're going to push as hard as we can, and if we get down to Earth mass planets, that'll be great. But comets will be, I think, too low in mass.
Okay. So for Express, what is the longer term precision? Is the 5 centimeter per second from the laser frequency comb stable for long periods of time?
Yep. So there are some, you know, we're now looking at shifts of spectral lines or laser frequency comb lines at the level of 1/10,000th of a pixel. I think the point is that there are different classes of errors, and these are calibratable errors. So yes, Express is stable at the level of 5-6 centimeters per second over now the last year that we've been operating.